So, good afternoon, my dear students. My name is Dr. K.C.H. Apparao, working as an associate professor in mechanical department, Institute of Aeronautical Engineering, Hyderabad. Okay. So, in previous class, we discussed the design of heat exchanger by LMTD method. So, design of parallel flow heat exchanger by LMTD method, design of counter flow heat exchanger by LMTD method. So we discussed the design of heat exchanger by LMTD method. So now we'll see the effectiveness method, another method or alternative method of the LMTD method. So you know that we have already LMTD method, then why we have to choose the another method? Why you have to go for the another method? So there is some drawback in LMTD method. So we'll see that one. So effectiveness method, it is the alternate method for the heat exchanger. So simply it is called as the effectiveness NTU method. So NTU, you know that too. NTU is the number of transfer units. NTU is nothing but number of transfer units. Now we'll see. So why you have to prefer the effectiveness method or NTU method? Because we have already LMTD method. So the origin of this method is based upon the fact that, so in practice you know that just like outlet temperature of the heat exchanger, just like a fluid stream from a heat exchanger, so these are may not be available due to the heat exchanger being connected to the downstream processing units. So downstream processing unit is nothing but reactors and chillers. They are the etc. It means in some cases we cannot measure the outlet temperatures. It means TC naught, TH naught. This one is the cold fluid outlet temperature. So this one is the hot fluid outlet temperature. So we cannot measure the outlet temperature of the fluids because so these are being connected to the downstream processing units, just like reactors and chillers. Okay, so it means in this case, just only we know that the inlet temperatures, just like hot fluid inlet and cold fluid inlet. So there are two parameters for solving for the design of heat exchanger by LMTD method, we should require the four temperatures, just like inlet temperature of the fluids and the outlet temperature of the fluids. So it means hot fluid inlet and hot fluid outlet and cold fluid inlet and cold fluid outlet. Okay, so we should require four temperatures. It means inlet temperature of the fluids and the outlet temperature of the fluids. Then we can design the heat exchanger by the LMTD method. Okay, so but in this case, just like we have only two temperatures. It means inlet temperature of the hot fluid and inlet temperature of the cold fluid. So we cannot measure the outlet temperature of the fluids, just like cold fluid or hot fluid. Okay. So it means only we have two temperatures. In this case, just like it is not possible to design the heat exchanger by LMTD method. So that is the drawback of LMTD method. Then you have to choose this alternative method, that is nothing but NTU method. So now we'll see the NTU method, how to design the heat exchanger, how to solve the heat exchanger problems by the NTU method. Okay. So we will derive the rate of heat transfer through NTU method. We will see that one also. So just like this is the conclusion point, you can see here, just like. So it means in some cases, just like, so this is case, only 2 out of the 4 temperatures from the heat exchanger may be available. So in this case, LMTD is not preferable for the design of heat exchanger. So here in this case, we will prefer the NTU method. Okay. So now we'll see. So you know that LMTD, in this case, LMTD is not suitable. So how to prefer the NTU method? Already explained that one. Now we'll see the effectiveness. You know the formula. This one already we saw in uh, so pins. The topic of the pins already uh, discussed this one. You know that effectiveness. You know the formula of effectiveness. It is represented by epsilon, just like effectiveness is equal to actual heat transfer by maximum possible heat transfer. Actual heat transfer, you know that is the Q. Maximum possible heat transfer, it is simply represented by Q max. Okay. So there are some formulas to find the Q and the Q max also. So you know the formulas, just like according to thermodynamic principles or thermodynamics. So loss, you know the formulas. Q is equal to just like mHch into hot fluid inlet minus hot fluid outlet. Okay. So it is also very similar to mCCc into cold fluid outlet minus cold fluid inlet. So these are the formula for the finding the Q values according to thermodynamics laws. So same formulas we will see here. Just like this is the Q is equal to mHch into Tha minus Th naught. So hot fluid temperature differences. So we can see mHch is nothing but a capital Ch. So specific heat. So then uh, hot fluid inlet minus hot fluid outlet. So we can see like this one, 1 by Ch is equal to, so Thi minus Th naught by Q also. So this is the, with respect to cold fluid. So Q is equal to mCCc into Tc naught minus Tca. You can see, we can write like this one. mCCc is nothing but a specific flow rate like this. Capital Cc into Tc naught minus Tca is equal to, we can rewrite like this one, 1 by Cc is equal to Tc naught minus Tci by Q. So this is the formulas. These are the formulas to find the rate of heat transfer. It means actual rate of heat transfer. But now we'll see what is the Q max. Q max, maximum possible heat transfer. Okay. So for the maximum possible heat transfer, so the maximum possible value that could be attained if the fluids were to undergo a temperature change equal to the maximum temperature difference present in the exchanger. So maximum temperature difference means, we know that Tha is the, so just like highest temperature point, Tc naught is the, Tca is the just lowest temperature point. You know that. So the temperature difference between these two, it means the hot point is the just like Tha minus Tc naught. So this is the difference. Okay. So which is the difference in the entering temperatures for the hot and cold fluid. So just like, so Tha minus Tc naught, Tca. So this is the maximum temperature difference, because Tha is the highest high temperature point and Tca is the low temperature point. You know that the difference between the uh, hot fluid inlet minus cold fluid inlet is the maximum temperature difference, we can say. So if it is maximum, so automatically uh, you know that capital Cc or so C, this will be minimum. If it is the maximum temperature difference, then specific heat, this specific flow rate, it will be C minimum. Okay. Then we will see the formulas like this one. Here, just like you know that counter flow graph like this one. This is the hot fluid inlet. So this one is the hot fluid hot fluid outlet. Okay, just like so you know that this is the cold fluid inlet. Okay. So you can see cold fluid inlet. So this one is the hot fluid, cold fluid outlet. Okay. Suppose the cold fluid outlet, if the cold fluid outlet is equal to hot fluid inlet, the graph is will be like this one. Okay. So the graph is will be like this one. It means so hot fluid inlet is equal to cold fluid outlet. Okay. In this case, so in this case, just like the temperature difference is maximum with respect to cold fluid. Okay, so it means so you know that rate of heat transfer Q is equal to with respect to cold fluid. So capital CC into TC naught minus TCA. Okay, so the TC naught is equal to THI according to this graph. Okay, then CC into THI minus TCA. So this is the maximum possible temperature difference. So if it is maximum, so this will be minimum. So the product of these two is equal to Q max. Okay, so this will be minimum. So in this case, CC is less than the CH. So it means CC will be minimum and CH is the maximum value. So in this case, we'll see one more condition, just like here you can see. So cold fluid outlet, cold fluid inlet. If the cold fluid inlet, suppose, is raised to hot fluid outlet like this one. So this is the cold fluid inlet is equal to hot fluid outlet. So then the formula with respect to hot fluid, you know that Q is equal to CH into THI minus TH naught. So this is the formula, you know that according to thermodynamic principles. So CH into THI minus TCI, because if the cold fluid inlet is equal to hot fluid outlet, so the temperature difference is maximum here. So then if it is maximum, this it will be Q max. Okay, so then this will be minimum. So CH will be C minimum. So in this case, just like CH is minimum compared to CC. So CC is maximum, CH is the minimum. So there are two conditions. So to get the maximum actual rate of maximum heat transfer rate. Okay. So one is the if the CC is minimum, so that is the one condition. If the CH is the minimum, it is the that is the another condition. So the maximum temperature difference is the temperature difference between the inlet fluid temperatures, just like hot fluid inlet minus cold fluid inlet. So we'll see. So by using these two conditions, we can solve the NTU method. Just like here, I'm taking first condition like CC. So cold fluid specific heat is less than the CH. So by using this condition, just like I'm going to solve the rate of heat transfer through NTU method. Okay. So for determine the effectiveness for the parallel fluid exchanger, just I'm assuming the C minimum is equal to CC. If the CC is C minimum, then C maximum is equal to CH. Okay. So you know that formula effectiveness is equal to actual heat transfer by maximum possible heat transfer. So effectiveness is equal to Q by Q max. Okay. So just like I'm taking the formula with respect to cold fluid, because I'm assuming C minimum is equal to CC. Okay. So you know that there are two formulas for finding the rate of heat transfer. P is equal to MHCH into THI minus TH naught. So MCCC into TC naught minus TCA. Just like in that, we are choosing the with respect to cold fluid. So then Q is equal to capital CC into Th naught minus Tca. So you know the formula, just like C minimum into inlet temperature differences, Tha minus Tca. Here C minimum is equal to, you know that C minimum is equal to Cc. So if it is Cc, this Cc, C minimum both are same, then you can cancel that one. Then effectiveness epsilon is equal to, so cold fluid outlet minus cold fluid inlet by hot fluid inlet minus cold fluid inlet. So this is the formula. You can assume this is the equation 1. So this equation is used to eliminate the temperatures from this equation, from the derivations. Okay, so you can replace the temperatures by the alpha by epsilons. Okay, so just you have to remember equation 1. Now we'll see the one more equation. So that is the, you know that these two formulas. So Q is equal to mHCH into Tha minus so hot fluid temperature differences. Then CH into Tha minus Th naught. You can write mHCH is equal to capital CH. So similar way, so capital Cc into Tc naught minus Tca. Okay. So here just like you can rewrite this formula. You know that so mH CH Tha minus Th naught is equal to MC Cc into Tc naught minus Tca. Tc. Okay. So you can rewrite like this one, just like turn this term this direction and turn this term this direction, just like mH CH by MC Cc is equal to Tc naught minus Tca by Tha minus Th naught. Okay. So otherwise you can write like MC Cc by mH Ch is equal to, so Tha minus Th naught divided by Tc naught minus Tca. We can write like, so you can assume that this is the equation 2. So there are two equations. Equation 1 is the previous one, already saw that epsilon is equal to capital CH into, so this one is cancelled, Tc naught minus Tha by okay. So Tc naught minus Tca by Tha minus Tca. So this is the form. This is the equation 1. This is the equation 2. Okay. So equation 2. So you can see this equation like this one. Okay. So equation. So this is the equation. Okay. So by using this formulas, you can rewrite like this one. This C minimum by C max is equal to, so MCCC by MHCH is equal to, so Tha minus Th naught by Tc naught minus Tc. So this is the equation 2. So by using equation 2, we can eliminate the just like outflow, just outlet temperature, just like hot fluid outlet Th naught and Tc naught. So these two will be eliminated by using this equation 2. By using the equation 1, we can eliminate all the temperatures and we can replace the temperature with effectiveness symbol epsilon. So these two equations are very important. By using these two equations, you can derive the formulas. Okay. So remember these two equations. Now we'll see. You know that this is the formula. So this is already we derived this one in LMTD method. Just like I'm taking that formula directly. Just if you have any doubts, just you can refer the LMTD method for the design of heat exchanger, especially parallel fluid exchanger. Otherwise, just like counter fluid exchanger also. Just I'm taking that formula. So ln delta T2 by delta T1 is equal to minus UA 1 by CH plus 1 by CC. You know that this formula. Okay. So just like you can UA by just I'm taking CC is the C minimum. Just I'm taking the common term. Then this will be so the 1 plus C by CH. Just like here we can see. Okay. So ln so TH naught minus TC naught by TH minus TC is equal to minus UA by, just like I have taken the C minimum is the common term. Then 1 plus C minimum by C maximum. C minimum is nothing but CC. C maximum is equal to CH. You know that. Okay. So you know that minus UA by C minimum, it is called NTU, number of transfer units. You can represent by NTU term, otherwise you can represent small capital N also. Okay. Then the formula will be like this one. Okay. So log of TH naught minus TC naught by, so THA minus TC is equal to, so this is nothing but NTU, so minus NTU into 1 plus C minimum by C maximum. You can consider this one C minimum by C maximum. You can just like represent this one capital C also. So if you represent this one, the formulas will be like this, minus N into 1 plus C. For the simplicity, just I am writing like this one. Okay. Just remember that. Okay. So then the formula is equal to, if you just like send this log to the another side, then it will be exponential. So exponential of just like minus NTU into 1 plus C minimum by C maximum. Okay. So then for eliminating these temperatures, just like we will use the equation 1 and equation 2. Now we'll see how to eliminate that one. So just like you know this formula, just I am rewriting this formula is equal to minus TCI and plus TCI. Just adding the cold fluid inlet and subtracting the cold fluid inlet. Now you know that for equation 1, so according to equation 1, so you can rewrite like this one. You know the equation 1 is equal to okay. So this is the equation 2. Okay. So equation 2 is equal to, you know that capital CH into THA minus TH naught is equal to CC into TC naught minus TCA. Okay. So by using this one, just like if you send this one THI, so this will be comes here CH. Okay. So then TH naught is equal to, the formulas will be like this one. Okay. So TH naught is equal to THA minus C minimum by C maximum. C minimum is nothing but CC. C maximum is nothing but CH. You know that values. So TC naught minus TCA. So substitute this value. So TH naught value in this formula here. If you substitute this formula here, you can get this formula like this one. So if you substitute the H naught value here, and if you rearrange this formula, just like we will get this one. So that is the THA minus TCA. Okay. Minus C minimum by C maximum to TC naught minus TCA minus TC naught minus TCA. So denominator is equal to same term. You can rewrite like this one. This one. Okay. So THA minus TCA by same denominator, THA minus TCA. So C minimum by C maximum to TC naught minus TCA by this term. So this term by same this term. So TC naught minus TCA by THA minus TCA. So then we can apply the equation 1 here. So you know the formula of equation 1. Equation 1 is equal to epsilon is equal to just like Tc naught minus Tci and Thi minus Tca. So this is the effectiveness formula. So in this case, we can substitute the epsilon value. So here Thi minus Tca by Thi minus Tca the same time. So this is the 1 minus. So C minimum by C maximum. So C minimum by C maximum into. So this is the Tc naught minus Tci by Thi minus Tca. So that is the epsilon value according to equation 1 minus. So same here also Tc naught minus Tci by Thi minus Tca. Here also epsilon value. So in both cases epsilon is the common term. If you take the common 1 minus epsilon, so then the formula is equal to 1 plus C minimum by C maximum. You can see the formula. So then the formula is will be like this one. Okay. So 1 minus C minimum by C maximum into, so this is called epsilon. So this is the epsilon. So epsilon minus epsilon is equal to exponential of minus NTU 1 plus C minimum by C max. So this is the same term repeating. So then the formula is will be like this one. So if you send this just like, so if you say here just like epsilon is the common term, just you can take the common and just to write the epsilon terms on one side, remaining terms into another side, just like the formula is will be like this one. So epsilon of 1 plus C minimum by C maximum is equal to 1 minus exponential into minus NTU 1 plus C minimum by C maximum. Then epsilon formula is equal to, so that is the final formula. So epsilon is equal to 1 minus exponential of minus NTU into 1 plus C minimum by C maximum divided by 1 plus C minimum by C maximum. So this is the final formula. You can rewrite like this one. Epsilon is equal to 1 minus exponential of minus NTU, it is represented by capital N, 1 plus C minimum by C maximum, so we can represent it by capital C divided by 1 plus C. So this is the final formula. So by using this formula you can find out the effectiveness epsilon values. Okay. So this is the just like method, LMTD NTU method for the design of the heat exchanger, mainly parallel fluid exchanger. Okay. So in next class we'll see the design of counter fluid exchanger by NTU method. So before just like going to that, just I want to explain one numerical. The formula is like this. Numerical. So same formula, just I'm repeating. You can see. Okay. So we'll see one numerical based upon the NTU method for the parallel fluid exchanger. Okay. So this is the numerical. A parallel flow heat exchanger is used to cool 4.2 kg per minute of hot liquid. So it means mass flow rate mH is equal to 4.2 kg per minute. We have to convert into kg per second. Kg per second. So minute means 60. Okay. Of specific heat also given, C small ch is equal to 3.5 kilojoules means 10 cube into joule per kg Kelvin. Okay. So inlet temperature of hot fluid also THI is equal to 130 degrees Celsius. Okay. So that is the data for the hot fluid. Next, a cooling water of specific heat. So another fluid is the water. So hot fluid is the just like two fluids. You know that heat exchanger means transferring heat from between the two fluids. One is the hot fluid, another one is the cold fluid. So hot fluid data is given. Now we'll see the cold fluid data. A cooling water. Cold fluid is the water. Specific heat of the cool fluid also given. It means so Cc, small c is equal to 4.18 kilojoule per kg Kelvin, just like 4.18 into 10 cube joule per kg Kelvin. Okay. Is used for the cooling purpose a temperature of, so cool fluid inlet temperature TCA is equal to 15 degrees Celsius as given. So and then the mass flow rate of the cooling water. So MC also given. MC is equal to, so 17 so kg per minute. So this minute should be converted into seconds. So 17 by 60 kg per second. So this is the data. Okay. And also overall heat transfer coefficient. So that one also U also given. So area is equal to, just like this one also, area also given. So now we have to find out the outlet temperature of the liquid. Next to outlet temperature of the water. So liquid means so hard fluid. So it means so TH naught you have to find out, and TC naught also you have to find out. Then you have to find out the effectiveness epsilon. So you know the formula of effectiveness also. Okay, you will see how to solve this numerical. This is the given data. Just like overall heat transfer coefficient also given. It is represented by U. Area also given. That is A. So mass flow rate is given. So you can have to convert into kg per minute, should be converted into kg per second. So this is the value. And the specific heat of the hard fluid also given. So it means so CH. So 3.5 kilojoule per kg Kelvin converted to joules. So it means kilo means 10 cube. You know that. So similarly, inlet temperature of the hot fluid. So inlet temperature also given. Hot fluid temperature 130 degrees Celsius. Next to specific heat of water, cold fluid. So Cc is equal to 4.18 kilojoules. Just convert into joules. 4.18 into 10 cube. So similarly, mass flow rate of the cool fluid also given. So 17 kg per minute converted into kg per second. Inlet temperature of the cool fluid also given. So that is the TCA is equal to 50 degrees Celsius. Okay. So you know that you have to find out the hot fluid outlet temperature, cold fluid outlet temperature, and effectiveness. How to find out this one. So before going to so here just like how to observe that one, there are only two temperatures are given. So inlet temperature of the hot fluid and cold fluid inlet temperature. Only inlet temperatures are given. Only inlet temperatures are given, then you have to choose the NTU method. If the four temperatures, it means inlet temperature and outlet temperature of the fluids. It means THA, TCA, and TH naught and TC naught. So four temperatures are given, then you can prefer the LMTD method. If only two temperatures are given, you have to choose the NTU method. Okay. So first of all, you have to find out the C minimum and C maximum. Which is C minimum, which is C maximum. So you know the formulas. So capital CC is equal to MCCC. Capital CH is equal to MHCH. So these values are given. Then you have to find out the capital CC and capital CH. Okay. So capacity rate of hot fluid. So capital CH is equal to MH small ch. Okay. So then the value is equal to ch is equal to capital ch is equal to, so 245 watt per Kelvin. So you can choose, this is the equation 1. Then you have to find out the capital Cc. Okay. So capacity rate of the water. So capital Cc is equal to Mc and Cc. Okay. So specific heat of the water is given. Mass flow rate of the water also given. Okay. Then capital Cc. So capacity rate is equal to, this is the value. You can observe the Cc is greater than the, this is greater than the Ch. Okay. So you know that Ch is equal to 245, Cc is equal to 1170. So So CH is greater, CC is greater than this is CH. So it means CH is the minimum and the CC is the maximum. So we can take the effectiveness formula, effectiveness value, or you can find the effectiveness value by using the formula which was derived one. Otherwise, you can find the effectiveness value by using the graphical method also, by using the data book. Just like I'm going to formula, we already derived this one. So effectiveness for the parallel flow is equal to, so 1 minus exponential of minus n into 1 plus c divided by 1 plus c. So this is the formula. So n is equal to, you know that formulas, minus ua by c minimum. So you know that c minimum is equal to ch. Okay. So c, capital C is equal to c minimum by c maximum. So c minimum is equal to ch, c maximum is equal to capital CC. So you know the two formulas. So by using these values, you can find out the effectiveness. We'll see how to find out the effectiveness. Okay. Just like here, direct values are substituted. So this is the 1.34, that is the NTU. NTU is nothing but minus UA by C minimum. Okay. U already overall heat transfer coefficient also given, area also given, C minimum, CH is the C minimum. So you know the all the values. If you substitute the values, you will get the NTU. So that value is equal to 1.34. Okay. So next to C. So C is equal to C minimum by C maximum. So C minimum is equal to capital CH. So capital CC. So C maximum is equal to capital CC. So you know the values of these two. Then if you find out that one, then if you substitute these values, you will get the C value. So C value is equal to 0.209. So if you substitute the NT values and the C value, you will get the effectiveness values. Effectiveness value is equal to 0.64. If you know the effectiveness value, then you can find out the outlet temperatures. Just like you know the two formulas, just you can use the two formulas and you can find out the outlet temperatures. So first one, you know that effectiveness is equal to actual heat transfer by maximum possible heat transfer. This formula you already know that. So Q by Q max. Okay. So here just like C minimum is equal to CH. So you have to take the formula, so which is related to hot fluid, because CH is the C minimum. So Q is equal to CH, capital CH into THA minus TH naught by C minimum into inlet temperature differences. Okay. So then CH, C minimum both are same. You can cancel that one. THA minus TH naught by THA minus TC. So this formula. Okay. So then here inlet temperatures values, you know that hot fluid inlet value is 130 minus TH naught, you don't know. And hot fluid inlet is equal to 130, cold fluid inlet is equal to 15. Okay. Effectiveness is equal to 0.64. So by using this formula, you can find out the hot fluid outlet. Okay. So hot fluid outlet is equal to 56.4 degree Celsius. So this is the. So now we'll see the another equation. This is the equation 2. You know that. Okay. By using this one, you can find out the full fluid outlet. So you know that C minimum by C maximum is equal to. So MCCC by MSCH. Otherwise, you can rewrite like this one. MCCC is nothing but capital CC by capital CH. Okay. So you know inlet temperature values. Inlet temperature of the hot fluid, you know that. Hot fluid outlet temperature, you know that. Cold fluid inlet, you know that. So you have to find out the cold fluid outlet. So you know that CC is the maximum, C max, you know that. CH is the C minimum. So you know the value of C. Okay. So if you substitute the values, then you will get the hot fluid cold fluid outlet temperature. So cold fluid outlet temperature is equal to 30.4 degrees Celsius. Hot fluid outlet temperature is equal to 56.4. Okay. So epsilon is equal to, this is the hot fluid outlet, this is the cold fluid outlet. Epsilon is equal to 0.6. So these are the result values. So in this way, just like we can solve the different numericals, so which are based upon the NTU method. Okay. So thank you for the watching this class. In next class, we will see the design of counter fluid exchanger by NTU method. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.